Good morning. I'm happy to be with you once again for this new lesson in our Sustainable Mobility course. Last week we saw how fuels are produced and how they are refined. We also saw the technical differences between gasoline and diesel fuels, but also the difference between gasoline and diesel engines. We talked about the main principle and the key elements of a four-stroke engine, so now we are ready to focus on the engine itself. When describing an engine, the main parameters are the fuel consumption, or its overall efficiency, and also the power and torque, and pollutant emissions. In this first lesson, we will be talking about the engine's efficiency, and at the end, about power and torque. But before discussing the engine's global efficiency, do you remember the four-stroke engine from last week? Well, now we need to go a little more deeply into the thermodynamic cycle of a four-stroke engine in order to better understand where the energy is being used. So, first question, what is a thermodynamic cycle? The formal definition says that a thermodynamic cycle is a sequence of thermodynamic processes that involve transfer of heat and work into and out of a system while varying pressure, temperature, and other variables within the system. Here you can see some familiar examples. The ideal thermodynamic cycle of a four-stroke engine is called the Otto cycle. The cycle is represented in a graph of pressure against volume, where the pressure represented is the pressure inside the combustion chamber, or what we call the in-cylinder pressure, and the volume is the volume swept by the piston. Please remember that the Otto cycle is an ideal cycle. You will see that each process can be related to each stroke of the engine. In process 0 to 1, a mass of air is drawn into the cylinder at constant pressure. This corresponds to the intake stroke. Process 1 to 2 is an isentropic and adiabatic compression of the air as the piston moves from bottom dead center to top dead center. This is the compression stroke. Process 2 to 3 is a constant volume heat transfer to the working gas from an external source while the piston is at top dead center. This process is in fact the instantaneous combustion of the fuel. Process 3 to 4 is an isentropic expansion which together with the combustion process corresponds to the power stroke. Process 4 to 1 completes the cycle by a constant volume process in which heat is rejected from the air while the piston is at bottom dead center. Finally, in process 1 to 0, the mass of air is released into the atmosphere in a constant pressure process. This is the exhaust stroke. The efficiency of this ideal Otto cycle, or thermodynamic efficiency, is the maximal possible efficiency that we can get out of an engine. The equation for the thermodynamic efficiency of an Otto cycle is defined as 1 minus 1 over the compression ratio to gamma minus 1, where gamma is the specific heat ratio of the gas Cp over Cv. From this equation, you can see that the engine's thermodynamic efficiency depends directly upon the compression ratio. Increasing the compression ratio will improve the thermodynamic efficiency. Now that we're talking about efficiency, we will go deeper into this concept. In simple terms, efficiency is a matter of how much energy we can use compared to how much energy we need to put in our machine. In other words, the overall efficiency is the ratio between the amount of useful mechanical energy available to power the car compared to the amount of chemical energy introduced into the engine through the fuel. Do you know roughly what is the engine's overall efficiency? We will discover this in a few minutes. You'll remember that in the engine, the fuel's chemical energy is converted into mechanical energy to power the car. The chemical energy available in the fuel can be calculated if we know the low heating value of the fuel. The fuel's chemical energy, or the amount of energy that we introduce, is calculated by multiplying the mass of fuel that goes into the engine times the low heating value. However, not all the energy available in the fuel is converted into useful mechanical energy to power the car. As you can imagine, there are several energy losses to take into account. But where does the energy go? Our starting point will be the fuel's chemical energy. The fuel burns inside the combustion chamber. Most of the time, and for different reasons, combustion is not complete. There is always some unburned fuel remaining at the end of combustion. This fuel goes directly to the exhaust pipe and its energy is lost. Of course, We try to optimize all engine parameters so that the amount of onboard fuel is very low. Still, in the best case, around 1 or 2% of the fuel is wasted due to incomplete combustion, and sometimes even more. Once the fuel burns, the heat produced by combustion is used in the engine thermodynamic cycle to produce power. The thermodynamic efficiency must be taken into account now. The thermodynamic efficiency, as we have seen, depends on the compression ratio. Roughly, we can say that around 35 to 40% of the energy is wasted when the fuel is used during an ideal engine's thermodynamic cycle. But this is the efficiency of an ideal engine cycle. You can well imagine that our engine is not an ideal machine, so it is impossible to make it work at an ideal efficiency. In real engines, the admission and exhaust phases are not instantaneous or at constant volume. There are heat losses in every stroke. Combustion is neither instantaneous nor isochoric. All these points are sources of energy losses that reduce the efficiency of the engine when going from the ideal cycle to the real cycle. Around 20% of the energy is lost here. Finally, we have the mechanical losses. This includes all the energy dissipated in friction between all mechanical parts and all the energy needed to drive the accessories of the engine. Mechanical losses count for around 5% of the total energy. After all the losses are computed, engines have a fairly low global efficiency. Indeed, the global efficiency can be as high as 35% in optimal operating conditions, 40% in the very best cases. Can you imagine? In the best case, only 35% of the energy in the fuel is used to drive the car, and the remaining 65% is lost. In the worst case, which is the case when your engine is running but the car is not moving, like when you're stopped at a red light, well then, all the energy supplied by the fuel is used to overcome all the energy losses. So the overall efficiency is zero. Most of the time, the engine's efficiency is constantly changing from 0 to up to 35%. In the next video, we will continue to discuss the efficiency issue. See you soon!